Well, hello everybody. Hopefully you're having a great day today. What I'd like to do with you today is I need to cover section 6-2 with you, which is called optimization. The assignment will be out of the book. It is also on the bottom of your class notes. But here's where I need to go very first with you. I need to take you for a trip down memory lane. I need to make sure that you remember how to find volume and surface area of some simple geometric figures. I know I only have find the expression that will find the surface area of this. Remember guys, the volume of this box, it's simply length times width times height. So if I'm picking on the volume of this, I'm going to have my 10 times my 3 times my 5. So it looks like 150 cubic feet in this case. Now, let's think about the surface area for just a second. The way I'd like for you to think about these is think about just the sums of the areas. So think about this. I'm going to find the surface area of this. Look at this front panel. It has a length of 10 and a height of 5. So for the front panel, I've got an area of 10 times 5. Now guys, there's also one in the back, so I'm going to double that. That takes care of the surface area of the front and the back. Now let's move on to the sides. Let's find the area of this panel right here. Well, it looks like it's 3 by 5. And there's one here, and there's also one over there. So I'm going to double that. Now to bring this home, I also need to think about the area of the top and the bottom. Well, if you look at the bottom, I've got a length of 10 feet and I got a width of 3. So I got something like this going on. Well, if I look at that, I'm going to have a 10 times 3, and there's going to be 2 of them. One on the bottom, one on the top. And of course now we would just add those together. So it looks like this is 100, looks like this is 30, it looks like this is 60. So I get a surface area of 190 square feet. So I need you to remember how to do that. My next is the exact same box, but I threw away the numbers. I need you to be able to think through that also. So here goes this. I'd like to figure out the surface area of this. And then I may come back and figure out the volume of it. Well, once again, let's pick on this front panel. I've got a length of 3x. I've got a height of h. So far, I've got 3xh. And there's 2 of them. There's one on this side, one on that side. So at the moment, I'm up to 6xh. Let's move over to this side now. It's got a length of x, a height of h, and there's 2 of them. So for the sides, I've got 2xh. The only thing I haven't picked on now, the top and the bottom. Well, so picture this. The bottom has a length of 3x, a width of x. Well, that's going to be 3x times x. So I've got 3x squared. And we've got 2 of them. So my formula for the surface area, I've got 3xh times 2. So I've got 6xh plus 2xh plus 6x squared. So my ending formula, 6x squared plus 8xh. Now what you'll have to do is be careful sometimes. Every now and then they'll say an open box. Well, if it's open, we are always going to assume that means the top. So if that happened in this case, instead of on this 3x squared times 2, I would lose that 2. That would change that to a 3x squared plus 8xh. If I look at the volume of this thing, my volume is going to be the 3x times the x times the h. So my volume is going to be 3x squared h. So there's what we got going so far. Another formula I'd like for you to look at real fast is that of a cylinder. So trip down memory lane on this one. The volume of this thing is going to be the area of the base, which is a circle. Got that circle down there, times the height. So the volume of this will be pi times r squared, which is 100, times the height. So it looks like the volume of this would be 2,000 pi cubic inches. Now for the surface area of this, what you got to remember for the surface area of a cylinder, really what you have, guys, is you have a circular top and a circular bottom, and then you have a rectangle on this inside there. This rectangle has a length of the circumference of a circle, which is 2 pi r. It has a height of h. So here's a formula for the surface area of a cylinder. I've got the area of the base, and I got two of them. So I've got 2 pi r squared. That takes care of the two circles. Plus, now to get this lateral area, it's going to be the circumference of a circle, which is 2 pi r, times the height of it, times h. So there's my formula for a closed cylinder. Here in a second, I'm going to make that an open cylinder. Well, all I'm going to do is I'm going to lose that 2. So here goes the surface area of this. I've got 2 times pi times r squared, so there's 100, plus 2 times pi times 10 times 20. This looks like I'm going to have 200 pi plus 400 pi. So it looks like this surface area, 600 pi inches squared. So the big thing I need you to remember there, the two circles, the top and the bottom, and then this is the lateral area, the side. I've got one more coming at you, then I'll get to the meat of the lesson. Here goes another one. It says, state an expression that will find the surface area of the following figure. Now this time, guys, it's an open cylinder, meaning that there's no top. That way we can put a plastic lid on it or something else. So here goes the surface area of this. It's going to be the area of the base, pi r squared, plus that lateral area, which is 2 pi r times the height. Since it's open, I don't have that 2 here. So it looks like I'm going to have pi times 16 squared plus 2 times pi times 16 times 22. So it looks like I'm going to get 256 pi plus, oh boy, 2 times 16 times 22 would be 700, add 4, 704 pi. So it looks like this surface area, 960 pi inches squared. Just on a little side note here, the volume of this is still pi r squared h. It doesn't matter if it's open or closed. The volume's going to stay the same. So that's just a trip down memory lane first. Now to get into the lesson. It's a tough little lesson. Today we'll look at methods of finding the maximum or minimum values of various problems, hence the word optimization. You'll be asked to find the dimensions that might maximize the area, maximize the surface area, minimize the surface area. A lot of times what you'll try to do, you'll try to maximize the volume, but you want to use the least amount of material to make that package. That's where we're going to go today. So peek at your number 1 here. It says find the dimensions of a rectangle that will have a perimeter of 150 feet but will maximize the area. On every one of these problems, we have what we call a constraint equation. The constraint equation sets your boundaries. It gives you what to work with. The primary equation is what you're trying to maximize or minimize. Well, in this case, check out what you have. I know my figure is going to have a perimeter of 150 feet. I also know that I'm working with a rectangle. So my rectangle's got a length and a width. The 150 goes with the perimeter. So here's my constraint equation. I'm going to say that 150 equal. That 150 sets up my perimeter. What's the perimeter of my rectangle? It's 2L plus 2W. That's my constraint equation. The primary equation is whatever you're trying to minimize or maximize. In this case, guys, you're trying to maximize the area. So my primary equation is area equal length times the width. Now here comes our steps. Every time you're going to solve your C equation for some variable. You get to pick it. So in this case, I'm going to come up here and solve this equation for L. So I'm going to have L is 150 minus 2W divided by 2. So L is going to be 75 minus W. I just simplified. Your next step is you're going to go ahead and plug that back into your primary equation. So I'm going to put sub into your primary equation. Meaning this. Here's going to be my next little step now. I'm going to take this primary equation which says area equal length times width. I'm going to go area equal my L, which is now 75 minus W, times W. The reason we've done those steps so far, now instead of working with two variables, I'm working with one variable. Your third step, you're going to simplify this. Your fourth step is you're going to find the derivative, and you're going to set that equal to 0. That's going to give you the dimension that you want to work with. So here goes. I've now got area equal 75W minus W squared. I'm going to find the derivative of this and set it equal to 0. So I'm going to go 0 equal 75 minus 2W. And we're going to solve this for W in this case. So my W value is going to be 75 over 2. I subtracted 75 and divided by negative 2, or 37.5. So now what do you have? Come back up and look now. That means my width is going to be 37.5, and it looks like my units are feet. To get your length, take 37.5 and plug it right back into your L equal equation. So 75 minus 37.5 is 37.5. So the dimensions of my rectangle that will have a perimeter of 150 but maximize the area, it's going to be a square with dimensions 37.5 by 37.5. You'll find if you have no other restrictions and it's rectangular, the way to maximize your area is going to be a square. But that's going to be the steps. They're going to be the same steps throughout the rest of the day. So here goes your number 2. I'll try to pick the pace up a little bit now. It says find the dimensions of a rectangle. So once again, I'm going to come over and sketch a rectangle and label it. Length and width. You can label it however you want. That will have an area of 300. Right there is my constraint. My constraint is talking about the 300, which deals with area. So go get your area equation of the rectangle that I just drew. So 300 equal length times width. My primary equation is whatever I'm trying to minimize or maximize. In this case, I'm trying to minimize the perimeter. So what do I need to do? For my primary equation, I need to write an equation for the perimeter of this rectangle. So the perimeter is going to be 2L plus 2W. So there's where we are so far. The next step, come into your C equation, your constraint equation, and solve that for either variable that you want. I'm going to solve it for L. So length is going to be 300 divided by W. So now here goes the work of it. I've got my primary equation that says perimeter is 2L plus 2W. I don't like two variables, so I'm going to sub that in. So I've got my perimeter is 2 times L, which is 300 over W, plus 2W. Now look at what you got. I got one variable. I got the W's. Next step, we're going to simplify this. So I've got 600 over W plus 2W. We're going to set that, well, we'll find our derivative, and we're going to set that equal to 0. So the derivative of this looks like negative 600 over W squared plus 2. And I need to set that equal to 0. So at this moment, one critical point's 0, but if I had a side of 0, I have nothing. So the 0 doesn't matter. I'm going to move the 600 over W squared to the other side. And then I'm going to cross multiply. So I've got 2W squared equals 600. I'm going to divide both sides by 2 and get W squared equal 300. And I'm going to square root both sides. So my width is going to be the square root of 300, or square root of 100 times square root of 3, 10 radical 3. So at this moment, I know my width. Now I need my length. So I'm going to bring that right back into here. So my length is going to be 300 divided by 10 divided by radical 3. 300 divided by 10 radical 3. If I think about that, take out a 0, that's going to be 30 over the square root of 3. I'm going to show you something here. Let's get rid of that radical 3. So I got 30 radical 3 over 3. My length is also 10 radical 3. So the answer to my problem here is going to be 10 radical 3 feet by 10 radical 3 feet. Once again, a square. If you're asked to minimize the perimeter but maximize the area, it's always going to be a square if it's got to be a perimeter, or if it's got to be. Otherwise, a circle beats a square. Okay? So there's 2 down. Now I'm going to get into some volume type equations. So what I did for you is I've given you a box over here. So let's read it. It says, a manufacturer wants to design an open box. That's important. No top. An open box that has a square base. That's also key. Here's what I'm going to do. As soon as I know it's a square base, I'm going to come over here and call this X by X. Now the height may be the same, but it may not. You can't assume that. So I'm going to call the height H. A cube would do the best if it wasn't an open box. So I've got it labeled. So now let's go to it. A manufacturer wants to design an open box that has a square base and will hold 350 cubic inches. Cubic inches deals with volume. So my constraint equation is going to be 350 equal, go get the volume of my box, X squared H. While I'm here, I know we're going to have to solve this for a variable. We're going to solve this for H. Otherwise, you got to have to work with the square root. So H is going to be 350 over X squared. So I've worked with my constraint equation. Now for my primary equation. Find the dimensions that will minimize the surface area. So for my primary equation, I've got to go get an equation for the surface area. So see if all this makes sense. I've got the base, which will be x times x, and the top is open, so I'm not going to double it. So I've got an x squared for the area of the base. Now for the side, my side is x times h, and I've got 4 of them. 1, 2, 3, 4. So my surface area is x squared plus 4xh. There's my main tools. Here comes my next step. Take your surface area equation, which is x squared plus 4xh. Sub in whatever you solve for from your constraint. And we solve for h. So I'm going to have surface area is x squared times 4x times 350 over x squared. Let's simplify that. So I've got surface area is x squared, oops, that's plus 4 times 350 is 1400. I've got an x and an x squared on the bottom, so that's going to leave 1x on the bottom. Our next step, find this derivative, and we're going to set it equal to 0. So the derivative of x squared is 2x. The derivative of 1400 over x is going to be minus 1400 over x squared. Once again, one of my critical points could be 0, but that's not going to help us any. So here's what I'm going to do next. I'm going to move this to the other side. So I've got 1400 over x squared equal 2x over 1. I'm going to cross multiply. So I've got 2x cubed equal 1400. Oops, I said 2x cubed equal 1400. I'm going to divide both sides by 2 and get x cubed to be 700. I'm going to cube root the 700 by taking it to the 1/3 power. So I know my x value is going to be approximately 8.88 inches. 700 cube rooted. Now I need my h value. So I'm going to bring this number right here, the 8.88, right back into there. And I'll go 350 divided by 8.88 squared. And I'm going to get that my height is going to be about 4.44 inches. Now, to bring it home, to give the dimensions of the box, it's going to look like this, if I can find some room to write. It's going to look like this. I'm going to say that the dimensions, we always describe it in terms of length by width by height. So I'm going to say that it's about 8.88 inches by 8.88 inches by 4.44 inches. So there's the dimensions of the box. What will that do? It'll give me a volume of 350 cubic inches, but it will minimize the amount of material, hopefully saving the consumer some cost. On to your number 4. One just like it. A manufacturer wants to design, once again, an open box that has a square base. So pause for a second. Come over here and draw yourself a square base. And guys, if you don't have your own box, just sketch yourself one. You know, if you got your geometry, you can make it look nice. If not, no big deal. Something, as long as you have a visual. But I just, x times h, or x times x, and my height is going to be x. Now let's check out what we got. An open box that has a square base and a surface area of 108. The 108 this time is my constraint equation. So I'm going to go 108 equal. Now you got to go get the surface area of that box. So keep in mind it's open. So I've got the area of the base once again, which is x squared. And then I also have the area of the sides. So once again, guys, x times h, and I got 4 of them. So x squared plus 4xh. There's my constraint equation. While we're here, let's go ahead and solve that for something. Decide if you want to solve for x or h. Well, we're definitely going to solve for h. If I solve this thing for h, I've got 108 minus x squared all over 4x. There's a lot of things you can do with it from there. I'm going to leave it like that for a second. Now my primary equation, we'd like to maximize the volume. So volume equal x squared times h. So there's my main part so far. So now what are we going to do? I'm going to take my primary equation, which is x squared h. I'm going to sub in h. So I've got volume equal x squared times 108 minus x squared all over 4x. Now from here, there's a lot of different things you can do. What I'm going to do, because I think it'll be simplest for you in the video, I'm going to distribute this x squared for a second. So I've got 108x squared over 4x minus x to the 4th over 4x. So I distributed the x squared and just put them each over 4x. I think in the video, with me not there in class to talk you through it, I think that's going to be our easiest. Let me come up here now, and let's simplify this before we do the derivative. 108 divided by 4 is going to be 27. So I've got 27x, one of my x's is going to cancel off, minus 1/4 x cubed. Now I haven't done any calculus yet, guys. Now let's find the derivative and set it equal to 0. So I've got 27 minus 3/4 x squared. A lot of different ways to solve it. What I'm going to do is I'm going to subtract 27 from both sides. So I got negative 27 equal negative 3/4 x squared. I'm going to go ahead and multiply both sides by negative 4/3. So I've now got 108 equal x squared. How about 36? 3 goes into 27, 9 times 4 is 36. Duh. And then let's square root both sides, so I got x to be 6. So a lot nicer this time. So I know x is 6. I still need to go get my h value. So let's plug 6 right there. So I'm going to go 108 minus 36 divided by 24. And I'm going to get h to be 3. So the dimensions of the box, and we're in inches, so it's going to be 6 inches by 6 inches by 3 inches. There's the dimensions that will get me surface area of 108, but will maximize the volume. Kind of notice one thing again, guys. Notice how this square shows up whenever you want to maximize something. And then it looks like I'm 2 away. Just 2 away. Here goes my number 5. You know I had to throw a cylinder at you. It says a cylinder with an open top. And then once again, guys, I put a picture on the notes for you. If not, just draw yourself a rough cylinder. It doesn't have to be pretty. Like that one, that's not pretty. But at least it gives you something to see, something to label. So here goes. A cylinder with an open top is to hold 100 cubic inches of water. Well, there's my constraint equation. 100 equal, and that 100's talking about volume. So the volume of a cylinder, the area of the base, pi r squared, times h. Let's go ahead while we're here. Let's solve that for something. Let's solve that for h. So h is going to be 100 over pi r squared. My primary equation, we would like to minimize the surface area. So my primary equation is going to deal with the surface area. The surface area of a cylinder, the area of the base, pi r squared, the circle, and there's just one of them because the top's open, plus the circumference of a circle, 2 pi r, times how tall my cylinder is, h. So there's my tools. There's my tools. Next step, into our primary equation, let's sub in h. So I'm going to have pi r squared plus 2 pi r times 100 over pi r squared. Let's simplify this. So I got surface area is pi r squared plus 200. My pi's are going to cancel out. That's good. I've got an r on top and two r's on bottom, so 200 over r. So there's where we are for a moment. Next step, find the derivative and set it equal to 0. So I got 0 equal 2 pi r minus 200 over r squared. Let me come right here now. To solve this, I'm going to move this to the other side and cross multiply. So I've got 200 over r squared equal 2 pi r. When I cross multiply, I've got 2 pi r cubed equal 200. Which means I've got pi r cubed equal 100. To figure out what r is going to be 100 divided by pi cube rooted. So I'm just going to take that to the 1/3 power. If you run that through, guys, you're going to get r to be about 3.17 inches. But I still need the height of this cylinder. So I need to take this 3.17 and plug it right back to there. Be careful when you type this in. You need to go 100 divided by parenthesis pi times 3.17 squared. Close that parenthesis off, hit your enter, and you're going to get approximately 3.17. So moral of that story, if you're next time you're in Dillon's or Walmart and you're looking at canned goods, if it has the same radius and height, looks like it's in a 2-to-1 ratio, they maximize the volume while minimizing the surface area. Since it's a cylinder, you just need to state the radius and the height. So that's all we've got there. And then it looks like I got one more coming your way. It's a little different. It falls into the optimization constraint type equations, but it's a little bit different. So here's the story on this one. We did it right before Christmas break, if you remember. I gave you a sheet of paper, and then our job was to cut squares out of this so that we could fold it up and make a box. So here goes. A rectangular box is to be made out of a rectangular sheet of metal by cutting out squares from each corner and folding up the edges. The sheet of metal right now is 18 inches wide, so I know this part is 18 inches, and 24 inches long. Find the dimensions of the box that will maximize the volume, and then find the volume. So like I said, just a little bit different optimization problem. Well, here comes our constraint equations. I'm going to cut squares out of here. I don't know the dimensions of my squares, so I'm going to call all of those x. Well, my constraint equations, they're going to look a little bit different. I've got 3 of them this time. One constraint equation would be the new length of this. The new length of this is going to be 24 minus 2x, because I'm going to take away this length and this length. The new width of this is going to be 18 minus 2x, because I'm going to take away that and that. And the height of this box is going to be x. Those are my constraint equations. That's why I said it's a little bit different. My primary equation is going to be the volume that I'd like to maximize. And the volume is found by length times width times height. So there's where we are for a second. Well, here goes. I'm not going to solve for anything this time. But what I'm going to do is this. I'm going to say that my volume is my length, 24 minus 2x, times my width, 18 minus 2x, times the height. What do I need to do there? I need to FOIL these out. So I'm going to get volume to be 24 times 18. So I'm just going to FOIL this real fast, guys. I'm going to get 432. And I'm going to go ahead and distribute an x. So I went 24 times 18 times x. So I've got 432x minus 24 times negative 2, negative 48x squared, minus 36x squared, plus 4x cubed. So here's my volume equation for a second. I've got 4x cubed, I'm just going to put it in order, minus 84x squared, plus 432x. Woo! Now what do we need to do? I need to find this derivative and set it equal to 0. 0 equal 12x squared minus 168x plus 432. Normally I'd tell you to just factor this, but in this case we're not going to mess with factoring. Let's quadratic formula this, and if you do that, you're going to get approximately 10.6, or you're going to get approximately 3.39. Think about this real fast. Let's look at that 10.6. If I tried to plug 10.6 right there, 18 minus 2 times 10.6, I've done 2 things. 1, I've got a negative length, and 2, I just wiped out my box. So this is gone. So here's what I got so far. I know that my height is going to be about 3.39. That's what I'm going to cut these out for. To get my length's going to be approximately 24 minus 2 times 3.39. So my length's going to be about 17.22 inches. And to get my width, you know where I'm going now, 18 times 2 times 3.39. I'm going to get my width to be about 11.22. So the dimensions of my box, 17.22 inches by 11.22 inches by 3.39 inches. What's that going to do? It's going to maximize my volume if I'm going to cut out squares like that. So guys, that is section 6.2. We will spend a couple of days on this because I really like optimization problems, and these are kind of easy. I'd like to make them a little bit tougher. So good luck with the book assignment. It should be at the bottom or top of your page. Just in case it's not, let me make sure that you know what those are. I've got on section 6-2, I've got 9, 10, 11, 16, 18, 21, and 23. While I'm on this page, I will mention this. A couple of your problems out of your book, they're going to give you a figure like this. You have a rectangular pen that you're trying to maximize the area of, and you're going to put a fence down the middle. Well, when I do that one, when I label it, I'm going to call this a width, this a width, this a width, and what's probably easiest is I'm going to call this whole thing the length. That way when you talk about the area, it's still length times width. When you talk about the amount of material that you're using, it's going to be 2L plus 3W. You might also see one where you're doing a plot of land along a river. Well, once you do that, here's a width, here's a width, here's a length. So the amount of material that you're using, 2W plus L. The area of it, it's still L times W. So guys, good luck with that, and come in if you need any help.